This is the second part of connected particles, which is the last part of the forces and motion chapter of mechanics. We're going to be looking at systems that are connected by a pulley. And in this case, your particles aren't necessarily going to be going in the same direction, but it's similar in how you apply the techniques to work out things like forces and things that are missing. You're going to get some simultaneous equations as well. Just bear that in mind. This is typically how the question is going to go. So let's see an example. Typically for a pulley question, you're going to get the picture. Okay, so are we going to go straight to the picture pretty much and look at what's going to go on it. So two particles connected by a pulley. These are the masses, but the m here is an unknown that we're going to hopefully work out at some point. Then weights are going to be 2m times g and 3m times g. And as we had before in our previous questions, we're going to have tension in this string. And you can pretty much guarantee that this tension is going to be the same everywhere, but we'll discuss why in a moment. So tension, but also we're going to have tension pulling not just out of the particles, but out of the pulley itself. Okay, that's quite important. So 4 lots of tension, again, pulling away from the objects that they're coming out of. And then we've got, we're going to release the system from rest. Okay, we're going to let these two things go. And because this one's heavier, common sense would tell you that that's the one that's going to go down, and this one's going to go upwards. So we've got two different acceleration arrows pointing in different directions. However, because this string is inextensible, just like we had before, that means that these are going to be the same amount of acceleration. Okay, and again, you can pretty much guarantee for a question that that's going to be the case. Okay, just don't worry too much about it. But as long as you can justify it at the end, that's great. Now, I can't treat this entire system as a whole because these accelerations aren't going in the same straight line. Okay, one's going up, one's going down. So we're going to look at our particles separately. Okay, and we're going to get some simultaneous equations going because we've got two different unknowns. So using P, we're looking at just this stuff. If I put a box around everything that's acting on P, that's where our equation is going to come from there. And when we come to do Q, it's going to be all of this stuff. Okay, so let's write an equation down. Newton's second law is our best buddy. Sub in the values, take upwards to be positive, same as the acceleration. You've got t minus 2mg equals 2m times a. If you want to rearrange, you can, but that's fine just to go on with just for now. The equation using Q, this time it's all the blue stuff. T minus 3mg. Oh, sorry, we're resolving downwards, aren't we? We're resolving downwards towards the acceleration, so this is positive. 3mg minus t equals 3ma this time. Okay, so you typically get this kind of reversal of terms here because of that. There's your two equations put together. I want to solve for the acceleration. Now, because we've got this t and minus t here, I think it makes sense to add the equations together. Rather than do a horrendous substitution, if you add together, the t's will cancel out. So let's do that. Add them together. Minus 2mg plus 3mg is mg, and then you've got 5ma there. Now, happy days, m's everywhere. I can cancel the m's. I think I'm going to run out of space at the bottom because of that bar at the bottom, so I'll do it over here. M cancels with m, and then you end up with a equals g over 5. Okay, look for that cancelling there whenever you see it. Okay, typically you get to something like that at the end. So a is g over 5. Which is 1.96 as well. So that can now go on our system. We can put that on our diagram. Let's get rid of this as well. And then once we've done that, we can go back to one of these equations. Now we know the value of A, we can go back to maybe this one and solve for T in terms of M, which is there. Sub in your G and your A. Oh, and it doesn't say what that is at the bottom. That might be in the way, but you can see it on your own. It will come up here in a minute as well. There you go, 23.52 m. Okay, find the force exerted on the pulley by the string. So we've now got these two, if we look at just the pulley, we've got two forces acting on it in the same direction, thankfully, as well. So if we want the total amount of force exerted on it, you just add these two t's together. I know what the value is. I know it's 23.52 m, and we've got two of them, so add them together. 47.04. In year 2, in year 13, you're going to be doing this with different directions. Maybe this one's coming out at an angle. We'll deal with that when we come to it. But for this one, it's just adding them together. Okay. Right, now for this next part, we want the distance travelled by Q. This typically happens towards like part D and E. When it talks about distance and velocities of things like that, you know you're going to be using SUVAT. Okay, it's introducing that stuff. But all of this stuff is stuff that we can apply with SUVAT. Okay, particularly acceleration. I can use that when I need to. So Q goes down for 4 seconds. A is then going to go. Particle P is then going to go up for 4 seconds, and we're going to assume that it doesn't hit the pulley. It doesn't do anything to stop what's happening with Q. That's described up there. Okay, Q moves consistently. So let's think about particle Q. S is the thing we want, the distance. U is 0, and we know that because it says initially it's at rest. Okay, we're releasing it from rest, so U is 0. V is, well, we don't really care. I don't need that because I've got enough information with A, which is 1.96, and T, which is 4 seconds, and we can use these 4 values here. So there's the equation for those 4. I can plug my values in. And it goes. Calculate, and there's your distance. Okay, so that's how you work that out. Now, modelling assumptions. There's a fair few here you can list out. So the string is light. Look for these words in this paragraph. Okay, you can see the common ones that you tend to get. The string is light means it's got no mass. The string is inextensible. That means that the accelerations are the same on both parts of these particles. And also there's this new one here for a pulley. If a pulley is smooth, then there's no friction going around the top bit here, which means that the tension this side is the same as the tension this side. So that's the newest modelling assumption that you might want to write down just in case you need to refer to it. Okay, one more example, quite a bulky paragraph. I think we'll go straight to the picture after we've seen what the questions are. Okay, and again, in an exam, you'll definitely get the picture, but you'll need to put the forces on, okay? So that's what we've got. We've got mass A, mass B, that one's hanging down. That's the height. You've got the weight of A and a normal reaction force because A is resting on that plane there, so we've got that force there. There isn't one for B because it's not resting on anything yet. There's this frictional force over here that's talked about down here. You've got tension pulling out of A on this string. You can have tension pulling out of B as well, but also on the pulley as well. Outwards. Then when this is released, B accelerates downwards towards the ground and A accelerates this way towards the pulley. So you've got these 2 arrows in those directions. And again, they're the same because the string is inextensible. So same acceleration. And we're going to find it. So again, can't do the whole thing. Wouldn't make sense to do the whole thing because of these different directions. Let's look at one thing on its own. Okay, separate particles separately. Okay, so horizontally on A, those are the forces. F equals ma. Plug the things in. T minus 0.08 g equals 0.4a. Just a small point, make sure you don't put g's in your masses. Okay, that's the weight, not the mass. There's the separate equation for B, so we can put that in as well. And don't make the same mistake I nearly did earlier. So A is going downwards, I'm going to resolve downwards. 0.8 g minus the T equals 0.8 times A. Okay, put the equations together. Looks like we can add these together again. Okay, T is going to cancel out. So there we go. That's what's happened there. And then we can divide by 1.2. And again, it's blocked, but it will come up here in a second anyway. It's 0.6 g. Okay, that's now been added to the picture. We've got 0.6 g there and there. I want the velocity at which B hits the ground. Okay, velocity implies we're going to be using SUVAT. So we can do everything on the particle B. We're told the height here to the ground, 0.5 meters. Resolving downwards as well, if we can. U is 0 because again released from rest. Make sure you're looking out for these in the big paragraph. Velocity is what we want. A we just worked out 0.6 g, and time we don't really care about time. Okay, it's just the first 4 we don't want to look at. Think about which equation uses these 4, and hopefully you've got a bit of fluency now, and you can kind of think about which one that's going to be. And voila, there's the equation. That's the one that uses those 4. Plug the numbers in. Sub in the values. We're after V, so that's going to stay there. Calculate, square root, and done. 2.42 meters per second. Okay. Then finally, this is talking about particle A now. Okay, the distance travelled by A before it comes to rest. So what's going to happen is things are going to change once this B hits the ground. Okay, B's accelerating towards the ground. When it hits the ground, the effect on the string is that it's going to become slack. I'm going to do that in a minute. So you've got to imagine now that this string is now slack. Okay, which means that the tension pulling it along is going to be 0. Okay, so we're going to get rid of this t when we do our calculation. Right, B's travelled 0.5 meters. That means A is going to move by the same amount as well. When B hits the floor, A will be moving at speed. So there's going to be some kind of velocity that we're moving at, and then the string goes slack, and it's going to kind of skid to a halt, okay, before it hits the pulley. And we're going to work that out. So what we need is the deceleration of A at the moment when B hits the ground. So we're going to do that. We're going to put all our things in. However, as we said before, t is 0 because the string is slack. So we've only got this force here, that's a frictional force. We can work out the acceleration when the string goes slack. That's minus 0.2 g. Then that's going to change. So to get it to a skid to a halt, that's the deceleration caused by the friction. We can work out the distance it travels to come to rest. But we've got to remember as well that there's this 0.5 that we're going to add to the end because A is also going to have moved 0.5 as well. So let's see that first. S is what we want. U is 2.42. V is 0 because we want it to stop. And A is minus 0.2 g. And time we don't really care about. So here we go. Here's the same equation again. Sub in the values. This initial velocity of A, remember, we've worked that out before. That's what we worked out for B. Because the velocity that hits the ground at is the same velocity that A is going to be moving at as well. Sub the values in, calculate S on the end there, and S is 1.5 meters. So that's the distance travelled after B's hit the ground, but add the 0.5 as well, and that gets you to 2 meters. Okay. And that's it. That's that chapter done for connected particles, and that finishes off forces of motion. Right, have a great day, Year 12. Thank you very much.